30 years after its inception, the James Webb Space Telescope was launched from French Guiana on Christmas Day. 2 years ago, on December 28th, it passed by the Moon. On January 24th, it fired its engines for 5 minutes before entering its final orbit, which is 1.5 million kilometers away from Earth. After months of tedious setup, it finally generated its first image on July 12th of last year, showing us distant galaxies for the first time as they appeared more than 13 billion years ago. Since then, the Webb telescope has continued to build upon this incredible foundation. It appears that the threshold has been lifted once more, and Webb is ushering in a new era of astronomy and space exploration. Its most recent photographs serve as proof of both humanity's capacity for discovery and its complete insignificance. Join us as we explore the new image captured by the James Webb Telescope that reveals the secrets of the universe. In actuality, telescopes are not physically peering back in time when they observe the light from distant galaxies. No one is able to directly gaze at the past because it no longer exists. Instead, the telescopes are observing a beam of light's current pattern. This beam of light has been essentially undisturbed for millions of years as it moves through the mostly empty vacuum of space. As a result, the pattern of this light beam at the present time is the same as the pattern it had when it was first produced by the far-off galaxy millions of years ago. We can therefore infer about the galaxy's appearance millions of years ago by observing a beam of light in its current state. It's comparable to printing out a baby photo of your daughter and then looking at it 10 years later. You are metaphorically looking back in time when you look at the printed photo to see what your daughter looked like as a baby. However, you are not actually seeing back in time. Your daughter is not a baby anymore, and she doesn't have a baby self anywhere in the universe. Instead, you are viewing a current light pattern that was produced by the printed photograph's inks reflecting the light in the surrounding space. Imagine, for example, that some acid spills on the image and a large white dot appears above your daughter's head. When gazing at the image, you would have to assume that your girl was being watched by a UFO or a ball of lightning 10 years ago if you were literally peering back in time. However, you're probably intelligent enough to know that you are not actually looking back in time but rather at a current light pattern that no longer precisely resembles the pattern of light from when you shot the photo 10 years ago. Similar to this, we can only infer the past from present-day light beams hitting observatories directed at far-off galaxies. If the light has not altered through time, a more accurate portrayal of the past would result from the light from distant galaxies changing as it travels. This change would have to be in ways that humans can comprehend and subtract from the redshift that results from the universe's expansion. Fortunately, since the redshift is now well understood, it is possible to shift the light pattern back by the proper amount to provide an accurate picture of the distant galaxy at the time the light was emitted. From just a few galaxies that were previously known to exist in the period, the James Webb Telescope, JWST, has now revealed hundreds of ancient galaxies that might be among the first inhabitants of the universe. According to a recent study, these very young galaxies displayed intricate structures and star formation clusters as early as 600 million years after the Big Bang. The study is a result of international cooperation known as the JWST Advanced Deep Extragalactic Survey, which collected data over the course of a month from 2 inconspicuous regions of the sky, one in the vicinity of the Fornax cluster and another in the constellation OSA Minor. Over 700 recently discovered young galaxies in this area provide insight into the early universe. If you took the whole universe and shrunk it down to a 2-hour movie, you are seeing the first 5 minutes of the movie. Kevin Hain, an assistant research professor at the Stewart Observatory in Arizona and a lead author of the new study, said while announcing the discovery. These are the galaxies that are beginning the process of creating the constituent parts and complexity of the modern world. The origins of the early galaxies and stars, which gave rise to the diverse range of elements seen in the universe today, are clarified by these recent discoveries. Using Webb's data, Payne and his team discovered 717 young galaxies in just those 5 minutes, which indicates that the universe is between 370 million and 650 million years old. These galaxies are all already thousands of light years across, have intricate structures, and are giving birth to stars in numerous clusters. Previously, the earliest galaxies we could see just looked like little smudges. Yet those smudges represent millions or even billions of stars at the beginning of the universe. Now we can see that some of them are actually extended objects with visible structures. Nearly all of the main space telescopes, including Hubble, the Chandra X-ray Observatory, and NASA's now-retired Spitzer, have conducted substantial research on the two locations used in this study, collectively referred to as Good South. 93% of the newly discovered galaxies that Webb found during this survey had never been observed previously. Despite prior examination, only the brightest, most extreme instances of brilliant galaxies from the early cosmos were visible to us before. Now that the cosmos is still young and tumultuous, we are actually drilling down to more common everyday galaxies. There's been much discussion on how exactly that chaotic, extremely dusty environment became the transparent universe we know today. One popular theory holds that this stage of the universe's evolution, known as the Epoch of Reionization, happened about 400,000 years after the Big Bang, when the first generation of stars, estimated to be 30 to 300 times as massive and millions of times brighter than our sun, formed and illuminated the previously dark universe by dividing the cosmos's plentiful hydrogen atoms into protons and electrons. This ultraviolet starlight reionized the universe, a process that continued for 1 billion years after the Big Bang. Few researchers, however, believe that outflows from supermassive black holes, like the one in the center of our Milky Way, may have caused ultraviolet radiation from galaxies to escape, and as a result may have had a more significant impact on cosmic development than previously assumed. Now, a second JWST team that has been researching galaxies between 500 and 850 million years after the Big Bang, or between 5 and 8 minutes of the 2-hour movie describing the universe, believes it has the solution to the age-old query. In this next scene of the universe, we are starting to actually see the impact of galaxy formation on the composition of the large-scale universe. Galaxies in the very early universe were just far more chaotic in general in how they formed stars. In order to understand how starlight ionized the gas within those extremely early galaxies, this team examined the signals of star formation in those galaxies, a property that atoms ionized by starlight radiate when they have cooled and merged with other molecules. The researchers discovered that 1 in 6 galaxies at the time displayed severe line emissions in the galaxy spectrum. These emission lines show that early galaxies were actively producing stars, which led to torrents of ultraviolet photons being blasted into each galaxy. As a result, the early stars of the cosmos turned into the primary forces for cosmic reionization. In this study, it is claimed that in the very early universe, these strong emission lines are actually very typical. These remarkably strong emission line fingerprints, which indicate intense recent star formation, are present in almost every galaxy that we have discovered so far. They were excellent at producing hot, massive stars in these early galaxies. The team deduced from the same emission lines that galaxies in the early cosmos gave birth to stars in brief bursts and then went dormant. A deep field image of hundreds of galaxies, many of which were seen as they were in the early cosmos, was the first image the James Webb Space Telescope sent back in July 2022. Many folks weren't prepared for some of these galaxies to appear to be curiously deformed and twisted. It is an illusion in the Webb photos. These Salvador Dali-like galaxies that resemble melted candy are not how these objects appear in space. A further surprising feature of the Webb photos is the appearance of many galaxies in the same image, as shown in the image of the huge galaxy cluster RxJ 20229. Once more, this is an illusion. These galaxies do not actually have identical twins. How is that even possible? The same gravitational lensing mechanism is what causes these two separate Webb image features. Albert Einstein's original prediction of gravitational lensing, which functions as a magnifying glass for astronomers, was made more than 100 years ago. There are all examples of gravitationally lensed objects that are warped into repeating galaxies. Einstein's theory of general relativity, which contends that mass-having objects have an impact on the fabric of space and time, combined to form a single entity known as spacetime, predicts the phenomena of gravitational lensing. Imagine a stretched rubber sheet that has been covered in balls of varying densities. The rubber sheet is more severely warped by a ball with a larger mass. The same is true for massive objects that are embedded in spacetime. The more massive an object is, the more spacetime it warps, with galaxies and galaxy clusters being particularly extreme examples. When light from a background object, such as a star or galaxy, traverses this warp, the effect becomes extremely fascinating. Normally, when light moves in straight lines, light from a distant source bends because of the way mass warps space. As a result, the background object appears to be in a different part of the sky when the light reaches Earth. Extreme warping occurs when there is a large object between Earth and the background source, causing light to travel along various routes that are all warped to varying degrees. This modifies the light's arrival time and the length of the journey it travels before reaching us. It follows that a lensed object may appear at many locations during a single exposure. This can result in some intriguing patterns, such as crosses or, in the case of lensing with perfect symmetry, a light ring known as an Einstein ring, which are all composed of repeated instances of the same thing. According to the European Space Agency, galaxy clusters are not ideal intermediate lensing objects because of their messy form and absence of a concentrated distribution of mass. As seen in the Webb Deep Field view, this results in the background lensed object appearing warped as arcs around the lensing galaxy cluster. But these lensing artifacts are more than just fascinating objects to look at. Astronomers can benefit from gravitational lensing in a variety of ways. In addition to distorting background light, gravitational lensing has the ability to magnify background light, enhancing feeble light from extremely far-off objects like early galaxies. Gravitational lensing is therefore vital to Webb's study of the early universe. Additionally, lensing objects can reveal a lot about themselves through the patterns they produce when light flows through them. According to NASA, for instance, gravitational lensing can show the distribution of mass in galaxies and galactic clusters. In addition, the superhot gas giant exoplanet that orbits its star in less than one Earth day has evidence of water vapor in its atmosphere, according to the James Webb Space Telescope. The exoplanet WASP 18b is a gas giant 10 times more massive than Jupiter, the largest planet in the solar system. The planet's orbital distance of just 31 million kilometers around the Sun-like star WASP 18, which is around 400 light-years from Earth, is rather extreme. Mercury, the innermost planet in the solar system, orbits the Sun at a distance of 634 million kilometers. For comparison, this exoplanet is so near to its parent star that its atmosphere reaches temperatures where most water molecules disintegrate. According to a statement from NASA, the telescope's observing abilities are demonstrated by Webb's ability to resolve the leftover water signals, even while the surface of the planet reaches temperatures of about 5,000 degrees Fahrenheit. The spectrum of its atmosphere plainly reveals a number of minor but accurately measured water features. Given its extreme heat, most water molecules would be torn to pieces. Therefore, the fact that it is still present is a testament to Webb's amazing sensitivity. Other telescopes, such as the Hubble Space Telescope, NASA's X-ray Space Telescope Chandra, the Exoplanet Hunter TESS, and the now-retired Infrared Spitzer Space Telescope, have explored the exoplanet, which was identified in 2008. However, none of these satellite observatories had the sensitivity to detect the signs of water in the planet's atmosphere due to their subtlety. The water features in this spectrum were challenging to spot in earlier observations. The Webb observations allowed us to finally observe water features, which was incredibly exciting. WASP 18b is tidally locked in addition to being extremely big and near to its parent star. The James Webb Space Telescope, JWST, continues to revolutionize our understanding of the cosmos. By capturing unprecedented images and data, it allows scientists to delve deeper into the origins of galaxies, stars, and planetary systems. One of the most exciting aspects of JWST's discoveries is its ability to detect and analyze the atmospheres of exoplanets, providing insights into their potential habitability. Recent findings from JWST have illuminated the complexities of early galaxy formation. The telescope's high-resolution observations reveal not only the shapes of these ancient galaxies, but also their interactions and mergers, which played crucial roles in cosmic evolution. These interactions can trigger bursts of star formation, contributing to the dynamic and chaotic environments of the early universe. Additionally, JWST's infrared capabilities enable it to peer through cosmic dust clouds, uncovering hidden star-forming regions. This has expanded our understanding of how stars are born and evolve in different environments, challenging existing theories of star formation. The telescope's sensitivity allows astronomers to detect faint light from these distant objects, revealing the intricate processes that governed the universe shortly after the Big Bang. Moreover, the JWST's ability to map the distribution of dark matter within galaxy clusters is enhancing our knowledge of this mysterious substance that makes up a significant portion of the universe. By studying how light bends around massive objects, astronomers can infer the presence and structure of dark matter, shedding light on one of astrophysics' biggest enigmas. In addition, the telescope is contributing to the field of astrobiology by analyzing the chemical composition of exoplanet atmospheres. By identifying molecules such as carbon dioxide, methane, and even potential biosignatures, JWST is paving the way for future missions aimed at finding life beyond Earth. As JWST continues to deliver groundbreaking results, it will undoubtedly reshape our cosmic narrative, providing answers to fundamental questions while opening up new avenues of inquiry. The ongoing collaboration among international scientists will ensure that the knowledge gleaned from this remarkable observatory enriches our understanding of the universe for generations to come.